Okay, today's lesson, areas in the plane, part 1. So we've already considered how to calculate the area of a region between the curve and the x-axis, and now we extend this idea one step further to find the area of a region bounded by one curve and below by another curve. Big applications here. This is the starting of a big idea on how to do some complicated math problems, but we'll just start with some nice little area ones here, and the visualization should be pretty straightforward. So when one of the curves lies above the other curve, calculating the area between the two curves is actually pretty straightforward. We can find the area between the upper curve and the x-axis and subtract the area between the lower curve and the x-axis. So the first example jumps right in here. It says find the area between y equals x squared plus 1 and y equals x on the interval 1 to 3. So the area that they're looking for here is sort of colored in pink there, and it's got a little r in there. And they want to find the area between these two curves. And they've done a nice drawing of the picture here so you can visualize what's happening. The idea being is I'm going to first find the area between the parabola, y equals x squared plus 1, and the x-axis. Yeah, I'm going to include all this stuff, and I'm just going to find a nice highlighter color here that is sort of non-obtrusive here, and just in here, I'm going to find that whole area here. See the pink and the gray. I'm going to do all of that. And to do that, I'm just doing simply integral from 1 to 3. That's what they ask for, of x squared plus 1. And so antiderivative, 1/3 x cubed plus x, evaluating from 3 to 1. Put in the 3 there. Let's see, I get a 9 plus 3. In that bracket. And in the other bracket, I get 1/3 plus 1. So 12 minus 4/3. Was that 36/3 minus 4/3? 32/3. So that's the first area. That's the area from the parabola all the way down to the x-axis. Then I find the second area, which is just the gray part that I'm looking at there. It's just the part between y equals x and the x-axis. And so I'm going to do integral 1 to 3 of x dx. Antiderivative, 1/2 x squared from 1 to 3. And so I get 9/2 minus 1/2, 4. Second area is 4. And so if I want to find the area between, all I got to do is take area 1 and subtract area 2. I'm taking 32/3 and subtracting 4. That'd be 12/3. So I get 20/3. Nice. Pretty straightforward stuff to find the area between two curves, and lots of good practice here on finding the area of and the antiderivative and so on. Will the above approach still work if one of the or both of the curves lies below the x-axis? Are negative values going to affect us here? And the effect is no. It's not going to be a problem at all. You can just subtract it. And why or why not here? Take a look. If you've got an upper curve and a lower curve here, and just because one goes below the x-axis here, you're going to be subtracting those values. So in the Riemann sums, you're going to be taking the function value of the upper one, subtract the lower one. That'll be the area of the particular rectangle, because when you subtract them, if you're subtracting negatives, that means subtracting a negative will be adding on. So you're no problem there. And as you take the limit, you can take a shortcut here to the question I just did above, is you can say, okay, you can do the integral from a to b and just subtract the functions. They don't have to be separate entities here. It's not really a problem there. So this screen shows two things. One is that just because one of the curves goes below the x-axis, that's not going to affect the calculation at all. And the second thing is we didn't have to find each area separately and subtract them. This is showing that if you want to find the area between two curves, you can just subtract the two functions right off the hop and find the integral, saving yourself a couple little steps there. What do I mean by that? Let's go back up to this one here. I could have done this question by just going, okay, integral from 1 to 3 of x squared plus 1, subtract the x. Just subtract the two functions right off the bat there, and you would get the same answer that we got here. That would work, no problem. And that's what we'll do moving forward. So some examples. it says use this, that you can just subtract the two functions beforehand to find the area between them, to find the area between these two functions that I've got here. So the area we want, we got to take the integral from -1 to 1, f at x minus g at x. So it's 5 minus x squared, subtract this x minus 1. Just need a double bracket there to stay organized. And you can collect all those up and hopefully do some like terms that'll save some work here. So I get 5 minus x squared minus x plus 1. And when I simplify that, I get negative x squared minus x plus 6. Antiderivative. Let's see, negative 1/3 x cubed minus 1/2 x squared plus 6x. And I've got to evaluate that between -1 and 1. So let's see, plug in 1, I get negative 1/3 minus 1/2 plus 6. Second one, okay, when I put a -1 into this one, I get negative, so that's a 1/3 in that second bracket. And when I put -1 in there squared, I get positive, so I get negative 1/2, and I guess a -6. Keep going here. Negative 1/3, that'd be negative 2/6 minus 3/6 is negative 5/6 plus, I think I get 31/6 here. Maybe you need an extra step there and get your common denominators and get organized there. 2/6 negative 6 minus, let's see, 2/6 minus 3/6 is negative 1/6 minus 36/6. Negative 37/6. And when I subtract those, I get 68/6. Oh, that reduces down 34/3. You know, I did some of the work there in my head because just to prep you for the idea that there might be university courses where you're not allowed a calculator and you'll have to do some of that work in your head. But usually when it's no calculator, those numbers don't get completely crazy. And, you know, I can do some of that. And maybe you need an extra step there to get your common denominator practice back in. How would the solution be different if you were asked to find the total area enclosed by the two curves? Well, to understand the answer to that, I need to get a little sketch of the two curves here. 5 minus x squared is a parabola opening downwards, something like that. And x minus 1 is a line. I just want to tidy this up here. Move everything up a little bit. Unhappy with how that was looking. There's 5 minus x squared, something like that. And x minus 1 is a curve that has slope 1 and y-intercept -1. So I've got this line here. And so they asked us to find the area between -1 and 1, which was fine. But really, if you want the area enclosed by the two curves, I need to go from this x value to this x value, which it's hard to know what those things are. I mean, I've just drawn a stupid little sketch here, so you don't know what those two things are. So what you'd have to do is then go, okay, where do these two curves intersect? You'd have to actually solve this equation. 5 minus x squared, we want to know when that is equal to x minus 1. When I move that over, I get x squared plus x minus 6. Oh, that factors nicely. I mean, they don't have to, but this one does nicely factor. And these curves meet at, therefore, x equals -3. That sort of fits with my diagram. And, or x equals 2. Well, you know, not too bad on my diagram to sort of go. And so if you actually wanted to find the area between these two curves, you'd actually have to use limits of summation of -3 and 2 of, what was it, negative x squared minus x plus 6. So if you want to find the area between two curves and they don't give you limits to use like this question did, then you're going to have to find the intersection points before you even start, so you know what limits to use to find the area between, because the only area between here, and let me get that gray color out again here, there's the area between right there. And maybe I want to be a little less subtle there than I was in that previous question. There's the area you'd be after if you wanted to actually find the area in between that green spot in there. And so you need to know what the endpoints of that area are before you even start doing the limits there. So this question asks you to do the full thing. It says, find the area of the region bounded by the parabolas y equals x squared and y equals 2x minus x squared. So first, let's find the points of intersection. Let's find out where these two meet. Is I go x squared equals 2x minus x squared. So I get 2x squared minus 2x equals 0. A little common factoring here. So apparently these two parabolas run into each other at x equals 0 and x equals 1. To give you a visualization of what's happening here, there's the parabola y equals x squared. This other one's sort of a downward opening parabola, I don't know, something like that. And so now this little area that we want in between these two curves, I've now found the x values that bound it. It apparently is between 0 and 1. Better yet, I now know this one's the upper one. Which, okay, some textbooks make a big deal about which one's the upper and which one's the lower, and you got to go upper minus lower. The facts are, if you do it the wrong way around, you'll just get a negative answer, and you know that the area is not negative in this particular case. We want a positive area between these two. So if you do it the wrong way around, it's not a really big deal. You just take the absolute value of your answer is basically what you're going to do here. It is nice to know which one's the upper here, and I know because one opens upwards and one opens downwards. You could also test a point. You could plug in 0.5 into the two functions and find out which one's higher at 0.5, and then you'd know which one's the upper and lower. There's methods to handle which one's the upper or lower. In the end, what I want is this area has got to be the integral from 0 to 1. I've now found the endpoints of that enclosed area, and the upper is 2x minus x squared, and the lower is x squared, so I got to subtract that. And so I get integral 0 to 1. 2x minus 2x squared, like that. Antiderivative time. This is x squared, and this is 2/3 x cubed from 0 to 1. First bracket is 1 minus 2/3. Second bracket is 0, and I end up with an area of 1/3. Apparently 1/3 units is the area of that region bounded by those two parabolas. And we'll do a trig example just to have covered everything before you head off to the homework. Determine the area of the region in between the curves y equals sine x and y equals cos x from 0 to pi over 2. Well, we just need a little picture here so we know what's going on. From 0 to pi over 2, cosine starts at 1 and does this, whereas sine starts here and does this. So weirdly, we've got two different areas to find and add together. They want from 0 to pi over 2, and then they want the area between. So let me just color this in. We've got to find this area here, which I'm doing a awesome job of coloring in here. And we also want to find this area in here. So the big thing is, where do they meet? How am I going to break this thing up? We want to know when sine x equals cos x. And I chose this example on purpose because university profs love this little situation, because solving the equation sine x equals cos x is actually pretty straightforward. But it's not something we study a whole lot in high school at any point. So it's a equation that can be quite perplexing when you first see it. Is how in the world, because it's tempting to bring that cos x over and go sine x minus cos x, and then you're really nowhere, like knowing what to do with that, because it won't factor or anything like that. So this will come up at some point. A university prof's going to drop this one on you, because they just love this situation to see if you really know your trig. And the really simple trick to being able to narrow this thing down is just divide both sides by cos x. And how do you know it's cos x? Well, cos x does nice things to both sides of this equation. When you take sine x and divide it by cos x, you get tan x. And when you go cos x divided by cos x, you get 1. And then I'm just trying to find out when tan x is equal to 1. A little special triangle action there. So x is pi over 4. I only want that one answer, so I don't have to go through that crazy cast or anything like that. I just want the first quadrant here answer, so all I'm worried about is that angle in the special triangle. Well, after all that, then I want these two areas. I want one area from 0 to pi over 4. In that part, cosine is the upper, and sine x is the lower. Then I also need the area from pi over 4 to pi over 2. And then that's part, sine x is the upper, and cos x is the lower. Get my dx's on there. And the rest is pretty straightforward stuff. Antiderivative of cos is sine. Antiderivative of negative sine is cos. How nice is that? That's from 0 to pi over 4. Add to that, antiderivative of sine is negative cos. Antiderivative of negative cos is negative sine. Careful with your negatives here. Boy, that can mess you up if you aren't really careful with those two negative values there. So first bracket in this one, I'm plugging in pi over 4. So this is 1 over root 2, and this is 1 over root 2. Subtract. Plug in 0, I get 0 plus 1. I'll plug in 0 into each of those. Second set of brackets. Okay, negative cos pi over 2. Oh, cos pi over 2 is 0. So I get a 0. Don't worry about that. And negative sine x. Oh, that's negative 1 in that first bracket. And then subtract. When I put pi over 4 into each of these, I get negative 1 over root 2. And I get negative 1 over root 2. Subtract all of that. Yeah. Oh, I'm going to do these two areas separate just to really show one little thing that might have been obvious from the beginning here, but I just really want to show it here. I'll work on this area over here. This one's 2 over root 2 minus 1. And this one's minus 1. The negatives all cancel here, so I get plus 2 over root 2 when I put those together. See, the two areas are the same. I don't know if that's a big surprise to you. My picture isn't quite good enough to be able to go, oh yeah, they're obviously the same, but we do get the same area on both things here. So what I get is, let me rationalize those so you can see what happens. 2 root 2 over 2 minus 1 plus, we can just switch that to minus 1. We don't need the plus and negative anymore. Minus 1 plus 2 root 2 over 2, and 2 root 2 over 2 is just root 2. And so final answer here I get is 2 root 2 minus 2 is the total area of the green and the red put together. Now, sometimes we might bound this thing. We want to say, oh, just find the area for when they intersect between the y-axis and pi over 4. There'll be different setups that you have to think through about how to use these limits, but basically you're just using the limits to find out what x values to use in your summation, and then again upper minus lower. And again, textbooks make a big deal out of using upper minus lower because it can matter in certain applications if you've got these things mixed and matched a little bit. When you're first doing these things, don't get too wound up about it. If you get a negative answer, just go, oh, I must have done that wrong. How could I have known which one was the upper? So that you're ready for when it does matter. All right, some great practice on integrals there. If you're a little rusty on integrals, there's lots of great stuff there. So go through those questions carefully and have a great day.